So in this video, let us discuss about the LC oscillation. Suppose we have a capacitor, let's say a capacitor having capacitance C, which is connected across an inductor like this. This one is an inductor having inductance, let's say L. There is a electrical oscillation going on in here, and that is called the LC oscillation. That is, when a capacitor is allowed to discharge through an inductor, electrical oscillation happens, and we call that as LC oscillation, and we call this circuit as an LC oscillator. Suppose this plate of the capacitor is positively charged. There is a flow of current in this direction. Let's take I be the current at any instant of time. And what this current do to the inductor is it sets up a magnetic field around this inductor. Initially, there will be no magnetic field around the inductor, but with progress of time, the magnetic field in the inductor rises. Also, the charge in the capacitor decreases. Now, let at any instant, this is the most important point, because our derivation is based on this concept. See, we have EC. Let's take the energy at any instant of the capacitor be EC, and the energy at any instant of the inductor, let's call that as EI. Since there is no external source of energy, that is, no external source is supplying energy to this circuit. So energy is always oscillating between this capacitor and inductor. For example, let's say initially the capacitor has a energy of 40 joule and the inductor has no energy. And after some time, if the energy of the capacitor, let's say, it becomes 30 joule, and definitely we have a question where this 10 joule has gone, and the energy, this 10 joule of energy lost by this capacitor is actually gained by this inductor. Let's call that as E dash. In both these cases, we can conclude that the total energy, initially these two are the energies of the capacitor and inductor, so that the total energy is equal to 40 plus 0, which is equal to 40 joule itself. And in the second case also, this is the energy in the capacitor, which is 30, and the rest 10 joule is gained by the inductor, 40 joule. That is, at any instant, the total energy always remains the same. So our derivation is based on this concept. So we know the total energy, let's take that as E total, is equal to energy across the capacitor plus energy across the inductor. Clear? But we know the total energy always remains constant. So if we take this as equation 1, and if we take the derivative with respect to time, that is d by dt of total energy will be d by dt of energy across the capacitor plus d by dt of energy across the inductor. Clearly, there is no change in total energy, so that this dE total by dt will be 0, since total energy always remains constant. So we can take this as 0. Clear? And we know the energy across the capacitor at any instant will be Q square by 2C. We already derived this expression in the session before. If you have any doubt, you can go and check the video in the session, the energy stored in a capacitor. Similarly, the energy stored in the inductor is half Li square. Here I is the current, here Q is the charge. Clear? And I can apply these equations, the values of EC and EI in here, so that it will be d by dt of, instead of EC, I can write Q square by 2C plus d by dt of half Li square. Clear? Now, let me write the right hand side first. Here 1 by 2c is constant. So 1 by 2c d by dt of Q square plus here half L is constant. So 1 by 2L d by dt of I square is equal to 0. So this is equal to 1 by 2c. See, d by dt of Q square is 2Q. Then you have to put dq by dt. Since the variable in here are different, here it is Q and here it is t. That is when we have d by dt of x square, we have to write 2x, first find the derivative of x square, that is 2x, then you have to put dx by dt. Clear? Because the variables in here are different. So 1 by 2c 2q into dq by dt plus half L. Similarly, this will be 2I di by dt, which is equal to 0. d by dt of I square is 2I, then you have to put di by dt. Now, if you simplify this, we can cancel these 2's. Here also the 2 will get cancelled, so that q by c dq by dt plus Li di by dt is equal to 0. Now, let's call this as equation number 2. We have I is actually dq by dt. Now, what actually is di by dt? That is d by dt of this I is actually dq by dt. So dq by dt. d by dt of dq by dt, which is equal to d square q by dt square. So I can replace this di by dt with d square q by dt square. So the equation 2 becomes q by c dq by dt plus Li into d square q by dt square equal to 0. Now we have, see, this dq by dt is actually I. So I can write this as q by c I plus Li d square q by dt square is equal to 0. Now, this can be simplified as, let me write this term first, or I can take the I part outside, q by c plus L d square q by dt square times I equal to 0. Therefore, we have q by c plus L d square q by dt square is equal to 0. That is equal to, that is 0 by I is actually 0 itself. Now I can rewrite this as L d square q by dt square plus q by c equal to 0, which implies divide the whole term with L. Then we have L by L d square q by dt square plus q by LC, that is multiply L with the denominator or divide each term with L is equal to 0 divided by L. So the equation will become, this L and L will get cancelled. So d square q by dt square plus, I can write this as q into 1 by LC is equal to 0 by L is 0. So this is the differential equation of the LC oscillation. Clear? And we have this differential equation is of the form d square x by dt square plus omega square x equal to 0. This equation, this differential, I can write it like this also, d square q by dt square plus, let me write 1 by LC part first, q equal to 0. So this differential equation is of the form this d square x by dt square plus omega square x equal to 0. Comparing these two, you will get omega square, which is the angular frequency of oscillation, that is the coefficient of x. Here the variable is in terms of q. So the variable omega square, when comparing these two equations, you will get omega square equal to 1 by LC, which will give omega is equal to 1 by root of LC. Clear? Now, we have, according to Euler's equation, from Euler's theorem, or let's say Euler's method, we have the solution of this differential equation is of the form q equal to c1 cos omega t plus some c2 sin omega t. The differential equation of this form is actually, the solution will be in this form, that is q, or here x is equal to c1 cos omega t plus c2 sin omega t. Okay. Now we need to find the values of the constants c1 and c2. For that, let me write this on a new page, because right now the page is stuck. There is some error with this program. Let me write the differential equation again. We have d square q by dt square plus 1 by LC times q is equal to 0. And we know the solution of this equation is q equal to c1 cos omega t plus c2 sin omega t. Now we need to find the values of constants c1 and c2. Also we have omega is actually 1 by root of LC. Now we know during the initial stage, that is at t equal to 0, the charge in the capacitor is actually maximum. Before the discharge of the capacitor, the charge in the capacitor is maximum. So that is at t equal to 0, we have q equal to maximum, q0. Also when, let's find the value of c1 first, so that q, I can write q0 instead of q, c1 cos omega into t equal to 0, omega into 0 plus c2 sin 0 omega into 0, which means q0 equal to c1 cos 0 is actually 1. So c1 into 1 plus c2 into sin 0 is 0, which will give c1 equal to q0. That is c1 equal to the value of constant c1 is q0. Now, in the same case, when q is actually q0, we have dq by dt is actually 0. Which means, see, when you compare these two, when the value of the function is, derivative of the function is 0, then the value of q is maximum. For example, we have a function y equal to f of x. The derivative of f of x, y, that is f dash of x 0, means y is actually maximum. Okay, so let me derive this equation. So dq by dt is equal to d by dt of, you have to derive each term with respect to time, c1 cos omega t plus d by dt of c2 sin omega t. So this is equal to, c1 is constant. Now the derivative of cos, you can take the value of constant outside of the derivative. So c1, now cos omega t, derivative of cos is minus sin omega t. Now you have to put the omega. Plus derivative of cos omega t is minus sin omega t into, since there is an omega t, you have to multiply it with constant omega. So here also c2 will come out. Now derivative of sin is cos omega t into again omega. So this is equal to dq by dt. But you know dq by dt is actually 0. So 0 equal to c1 minus c1 omega minus c1 omega into sine of, here omega t is actually 0, plus c2 omega cos omega into 0. 0 is equal to, this value becomes 0 because sine 0 is 0, plus c2 omega into cos omega is, cos 0 is 1, which will give c2 omega is equal to 0, implies c2 equal to 0. Since omega cannot be 0, 0 by omega is actually 0. So we have c1 equal to q0 and c2 equal to 0. Now let's substitute these values in the equation 1 itself. Then we have the value of charge q at any instant is, c1 is q0, q0 cos omega t. No need to write the term with sin omega t because c2 is 0. So this is the value of charge at any instant in LC oscillator. Now we have current I is equal to dq by dt. Once again, if the charge in the capacitor decreases, current in the circuit increases because current flows because there is a decrease in charge in the capacitor. So I have to put a minus sign. So minus d by dt of, actually q is q0 cos omega t. So I is equal to minus q0 into d by dt of cos omega t. Since q0 is constant, so I can take that out. This is equal to minus q0 into derivative of cos is minus sin minus sin omega t into omega. So the current at any instant is equal to this, minus and minus will become plus omega q0 sin omega t. So this is the value of the current at any instant. Sorry, not I0, I. So current at any instant equal to omega q0 sin omega t. Now we need to find the value of the maximum current. From this equation itself, the maximum value of sin omega t is actually 1. So the current is maximum, that is I equal to I0 when sin omega t becomes 1. So the value of I0 is actually omega times Q0. Now we have omega, that is I0 equal to 1 by root of LC, since value of omega is 1 by root LC, times Q0. Clear. Also, I0 is equal to 1 by root LC. For a capacitor, we have the charge stored is equal to capacitance into maximum voltage. So, substituting this value in here, CV0, I can write the C as root C into root C V0. By here, root LC means root L into root C. Cancel this C, so that I0 will be V0 times root of C by L. Clear. So this is the maximum value of current. Also, the ratio of peak value of current to the peak value of voltage is root C by root L. Clear. It will be the ratio of the capacitance to inductance. Root of capacitance to inductance. Clear.